So I was talking about operators. So if H is a Hilbert space, how do you define an operator? So an operator A has the following thing to do. Okay, for any vector, okay, so we can talk about a functional space. So for any phi of x, okay, I'm just going to continue with my one-dimensional thing. So for any x in this Hilbert space, operator will actually act on this function to change this function to some other function. Yeah. For some psi of x, for some psi of x. So the action of what? So if you ask a question, what is the general action of any operator on an element of Hilbert space? Is that it will change it to some other element. Okay. So based on this, we can talk about two concepts. First concept is that we talk about the domain of the operator A. Domain of A, and denote it as VA. Okay, so the domain of an operator. Okay, so what do we define this domain as? Now, suppose let's say that you have let's say that this is your Hilbert space, and there are some elements of this Hilbert space. Okay. And let's say this is also the same Hilbert space. Now it so happens that there are many of these elements that are mapped onto the same Hilbert space, but let's say some elements are taken this out of this Hilbert space. Okay, that means these two elements are taken out. They are mapped to some functions which are not in this H, but there are certain, let's say this is also taken out. Okay, so these functions are not in H, but there are some elements of H which are mapped within H. Okay. So those elements are called the domain of H, domain of A. So what is this one? This is the operator A, which is mapping one state to the other state. So that means your dA is basically a subset of the Hilbert space, where this dA is defined as those psi of x in H, okay, such that A acting on psi of x is also in H. A acting on psi of H is also in H. So this is what we call as the domain of H. Okay. Now you can have some elements here. Okay, we can have some elements here which do not have a pre-image. That means there is A is not going to take any of these elements to these elements. Correct? So then we define another concept called range of operator A. So denote it as some R. Okay. So the range of A is something that So psi of x in H such that there exists a phi of x in H in such a way that
Sir?
a phi of x is equal to psi of x. Yeah.
Sir, just to avoid confusion, you can put H1, H2, no, sir, because sometimes people
No,
might
this
get.
is not H1 H2. It is the same H.
Oh, it is mapped to same H.
Yes. The space are same. But within
Okay.
that, you may have a situation depending on your operator that range and codomain are subsets of H. So here, this range of A is also a subset of H. And it may so happen that it is also equal to that H, but in general, it can be a subset. Okay. So we are now defining two concepts. One is domain of an operator, and the other is the range of an operator. Now we can define two operators. Okay. So two operators A and B are said to be equal. Okay. They are said to be equal if domain of A is equal to domain of B. They should have same domain. And their action on each state of their domain is same. That means we say that dA is equal to dB, and then for all psi of x in dA is same as dB, A acting on psi of x has to be equal to B acting on psi of x. Only if their action on each of the element is same, then only we can say that it is equal. Two operators are said to be equal only if their domains are same and their action on each state of their domain or each wave function, each function of their domain is same. So this is the definition of an equivalent equal if two operators are said to be equal.
Excuse me, sir.
Yeah.
So here do we take like that their range will be also same because the domain is same?
No, range need not be same because we
But
are not
then,
yeah. Tell me.
but if range is not same, then why, how we can say that the operators are equal? Because these operators are acting on a particular wave function and then they are producing a different result.
Yeah. What I'm saying is that we don't have to put it in the definition because this condition means that the range is same. No, we don't have to put that as a definition. If the domain is same and if this condition is satisfied that for all psi action of A is same as action of B, that means range of A is same as range of B, isn't it?
Yes.
It comes out as a consequence.
Okay.
So we don't have to insist that as a definition.
Okay.
Okay. So this
Excuse
is,
me, sir.
yeah.
Sir, what does it mean by same action by the two operators?
So you go back to our first thing that what does an operator do? For any phi, it will generate another vector, right? So another function. So like that, suppose if a psi of x is equal to some phi of x. Okay, let us say that. Then you ask what happens to b acting on psi of x. Then I should get that also as phi of x. I should get that also as phi of x. If I'm not getting that, then they are not equal. And
Okay, sir, I understand.
this should be true for all psi. For all psi of x in this domain. Okay. Now, just like we have this general notion in mapping, so an operator A is invertible if A is a bijective mapping. That means it is both 1, 1 and on. Bijective map means it is 1, 1 and on. So, if that is so, then you have A psi of x is equal to phi of x. That means there is only one phi of x to which this can be mapped. This implies you can get your psi of x as A inverse operator operating on phi of x. So that is something which we can define if this is both 1, 1, 1 and on. Now we will define a little more important thing that is very relevant to our subject of interest, quantum systems, namely talk about a linear operator. A linear operator. So an operator A is linear if the following things satisfy. One, suppose when you take A, act on some alpha times psi of x, alpha is some scalar, is equal to alpha, I can pull out A acting on psi of x. For any scalar alpha and any psi of x in the Hilbert. The second thing is when A is acting on psi of x plus phi of x, then this must be written as A on psi of x plus A on phi of x. For any psi of x, comma phi of x in the Hilbert. Okay. Now these two things, that if it is satisfying, then we say it's a linear operator. Now we can combine. Okay, so we can combine 1 and 2 in one statement. namely A acting on some alpha times psi of x plus beta times phi of x can be written as alpha times A psi of x plus beta times A phi of x. So many times in the textbooks you will see this condition is defined as the linear operator definition than these two conditions. But essentially this amounts to satisfying these two conditions. Okay, so this is what is a linear operator. Now, so since essentially within the context of the most general definition that we have talked about what an operator is, you could have defined operator as anything that you can actually map one function to another function. For example, let's look at some examples to get an understanding of the linearity. Let's say I have a function. So let's say a function A acting on some phi of x. So let's take this one. A function A acting on some phi of x is equal to, let's say, d phi by dx. This is taking a differentiation of this function phi of x. Now, obviously, this function will, suppose if I take sin x, I will get cos x. If I take tan x, I will get secant square x. So I'll get different functions. If I take e power x, I will get e power x. If I take 2x, I will get 2. If I take x square, I will get 2x, and so on. So input function is one thing and output function is something else. So this is an operator. Now you can check that this operator will satisfy the linearity condition. So this operator is a linear operator. Now suppose if I take an operation like this, if A is operating on phi of x is equal to some x into phi of x. This is another function. If you take x square, then it will become x cubed. If you take sin x, it will become x sin x. These are different functions. That is just multiplying by x. Now you can show that this is also linear. Now let's look at an example where a phi of x is equal to phi of x the square. That is, you are squaring that function. If I take 2x, I'll get 4x square, and so on and so forth. Now you notice that this is not linear. So this is a non-linear operator, because if you take alpha phi x, I will not get alpha out, but I'll get alpha square out. Okay, so this is a non-linear operator. In the same way, let's say that I have A acting on phi of x is equal to, let's say, e to the power phi of x. Okay, this is another function. If you take x, it will be e power x. If you take x square, it will be e to the x square, and so on. But this is also a non-linear operator. So linear operators are the ones which satisfy these two criteria, or a combined criteria like this, and other operators that are not linear are non-linear operators. Okay, so we have talked about the linearity of the operator. Then we will talk about something called an operation called adjoint of an operator. Okay, adjoint. Adjoint of an operator. A, and we denoted by A dagger. So this is A and this is A dagger. Now please understand this carefully, because this definition is very important. Now for any pair of elements of Hilbert space, say psi of x and phi of x in Hilbert space H. You take let's say psi of x and then operate A on psi of x. What happens? This will be another function, correct? Now take inner product of phi of x with the result of that. Okay, so you can see that action of A on psi of x gives another function. Now take inner product of that function with phi of x. That is whatever I have written here, I am writing in sentences. What will you get? We get a scalar. It is a complex number. We get a scalar. Now we are going to ask a question. Can I produce the same scalar by some operator acting on phi of x and then taking inner product with psi of x? Okay, so can I get the same scalar by some operator acting on phi of x and then taking inner product with psi of x? So what is that operator? That is called the adjoint operator. So if A dagger acts on phi of x and take inner product with psi of x, that is what you have. So this is the definition. This is the definition of adjoint. So an operator and its adjoint are related in this fashion. That is, if A acts on psi of x, so you take any. This is true for any any two. Okay, instead of this phi of x, psi of x, you could take some other functions f of x, g of x. But this relation is true for any pair. For any pair of elements of H, psi of x, phi of x. If this is true, then this is defined as the adjoint. Okay, now for finite dimensional Hilbert spaces, that is for finite dimensional Hilbert space, an operator is a matrix, because it is a mapping from, it's a linear transformation basically. A linear operator basically, a linear operator is a matrix. So that implies the adjoint is a Hermitian conjugate. That means if you have a matrix A and A dagger, okay, so let us denote a matrix like this. A matrix A dagger is nothing but the matrix A transpose, and then conjugate. This is called Hermitian conjugate. Transpose conjugate. Okay, so but we cannot do this for an infinite dimensional, infinite by infinite matrices. And if you want to find out the adjoint for an infinite dimensional matrices, this is the only way in which you can do it. Okay, now we can ask a question that how do we define this? How do we define this? Okay, so let us try to understand this one. Let's say that so consider L2 of R. That means it is a space of space integrable, square integrable functions. Okay, so consider L2 of R as the Hilbert space. As the Hilbert space. Now we want to, so we would like to find out, find the adjoint, of d by dx. Okay, just I'm still working with one dimension, so let's say d by dx. Find the adjoint of d by dx. So how do we do this? We have to use this definition. So this is the definition for our adjoint of an operator. Okay, so let us consider this. So for let's say f of x comma g of x in this L2 of R, f of x comma g of x. So let us consider this inner product of f of x with an operator A acting on g of x. Okay, so we are going to use this one, right? So that is equal to, we should have the operator A dagger acting on f of x g of x. Now start with the left hand side. You start with LHS. That is, you have f of x comma d by dx of g of x. Now, by definition of the inner product, this is equal to minus infinity to infinity. Remember, this is over the set of real numbers R dx f star of x into e by dx of g of x. Okay, so maybe it is more convenient to write this d of x. Now, I want to bring this operator from G to F. Okay, so that can be done by just doing an integration by parts. So I will do an integration by parts. So integration by parts. Integration by parts. So we will consider U is equal to f star of x and dv is equal to dg dx into dx. So what will be your v? V is equal to g of x. And what is your du? df star of x by dx. So I will get first uv term, that is f star of x into g of x from minus, this is the boundary term, minus infinity plus infinity, minus integral minus infinity to infinity ef star by dx g of x. Okay. Now, since so this is so since uh, so f and g are in L2 of R, that means they have to be square integrable. This implies that f of x or g of x will go to 0 as x goes to plus minus infinity. They have to be this kind of a well-behaved functions. So because of that, this particular term will vanish, and you can write this to be minus infinity to infinity minus df by dx, the star into g of x will get translated into minus d by dx operating on f of x comma g of x. So you see, I started with the left-hand side where this operator is acting on this d by dx. I got a result where this operator is acting on f of x. So this tells me that, so therefore, implies that d dx, the differential operators adjoint, is equal to minus d. So d dx is minus d by dx. So this is how we find out the adjoint of a given operator. Now I wanted to make some. Okay, so this is. And so at this level, I wanted to make a couple of remarks. So the first remark is that suppose in three dimensions. Okay, so in 3 dimensions, if you ask, so in 3D Cartesian coordinates, we have uh, this del operator, dagger, is equal to minus del operator. Okay, the del operator dagger is equal to minus, because d dx dagger is minus dy dx, d dy dagger is minus dy dy. Okay, so that is understandable. Minus del. But for example, suppose if you take, so consider your operator A to be dou by dou r, where r is the radial coordinate, in let's say spherical polar coordinate. Spherical polar. Now, suppose you want to, somebody is asking what is, so find the dagger of this dou by dou r. So we may jump into some conclusion saying that it is minus dou by dou r, because it is just because here dou by dou x, okay, is minus dou by dou x. So the question is it minus dou by dou r? Okay. So the answer is no, not minus dou by dou r. Now what is that? Now when you want to find this out, you have to talk about an inner product. Okay, so we start with some functions, so f of r, and so we have to ask a question that what kind of function, what kind of a space. So we ask a question. So here we have functions of r, the radial coordinate. That means we must talk about L2 of 0 to infinity, not the full r. Okay, L2 of 0 to infinity. These are the functions that we are interested in. So when we try to take these radial functions, so let's say you have two functions, call them as f of r and dou by dou r of g of r. So when I write down this inner product, I have to write it like this: 0 to infinity f star of r into dou by dou r into g of r. Now here is the important thing that is that we have to keep in mind. I cannot write simply dr because the radial integral measure is not dr but r square dr. Okay, so the radial integral measure is not simply dr but it is r square dr. Okay, so remember your volume element is r square dr sin theta d theta. This is your volume, so dv in spherical polar coordinates. So this part is the radial measure, and this part is the measure corresponding to polar angle, and this is the measure corresponding to azimuthal angle. So we have to keep this in mind, because this is, since I have specifically mentioned that this is a radial coordinate in spherical polar, radial coordinate in spherical polar coordinates, we have to use this measure. Now when you do this, so this is something little tricky. So you have to consider this r square together with this f star of r. So when you are doing integration by parts, okay, so when you are doing integration by parts, you have to do something like this. So consider your u is equal to r square into f star of r, and dv as dou g by dou r into dr. So then your v becomes simply g of r, and du becomes, there are two terms, notice, it is 2r into f star of r plus r square into df star by dr into dr. So that will be your d. So that is equal to, so I will have r square f star of r into g of r. This is evaluated between 0 to infinity minus integral 0 to infinity. I have 2r into f star plus r square to df star by dr. So this is my into g of r dr. This is what I have. But then, so this term will go to 0 because the lower limit is 0, and because of this r square that will become 0. Upper limit is 0 because this is L2 of 0 to infinity. So that part will go to 0. And then I have, so when I am writing like this, I have to pull out an r square and then keep this as an integration measure. So that is equal to integral 0 to infinity. I pull out an r square, then I have minus 2 by r minus dou by dou r. Okay, so this acting on f star of r into g of r square dr. So this measure I have to keep it same as the measure here. So this is basically equal to, if I write this as an inner product, I have minus 2 by r minus dou by dou r, this operator acting on f of r comma g of r. So what does that mean? That means the dagger dou by dou r dagger is equal to minus 2 by r minus dou by dou r. It's not simply minus dou by dou r. So one has to be careful that depending on what we are considering, we have to choose this dagger to be. You have to understand what is the integration measure in the definition of. So I also mentioned towards the end of my discussion on inner product that the inner product can be generalized by defining something called a weight factor. So you could have visualized this r square as the weight factor. Okay, so that is also another way to look at it mathematically. Now I will, yeah.
In the previous step, you missed the star. It's minus 2 by r minus dou by dou f star of r.
Yeah,
Is
yeah.
equal to.
Here I don't have to write because this is just a bracket. Okay,
Oh,
only when I write under integral, I need to write f star.
that's by notation convention. I mean the convention notation.
Yeah, yeah. Within the bracket, we don't have to put star. Only when the integration, we have to put star.
Sorry, sir. Okay, sir.
Okay.
Sir,
Yeah.
sir, in the previous example, del operator in the one dimension is anti-Hermitian, and in this three dimension, is it Hermitian, sir?
Okay, so I will come to this Hermitian business in a little while from now. So far, I have not talked about Hermitian. I'm only talking how to find the adjoint of an operator. Okay.
Okay, sir.
So we will define the Hermitian, non-Hermitian, all this a little later. So this is just to find the adjoint of an operator. Now we can. So I just want to leave two exercises for you to get a practice of this finding the adjoint. So exercise 1 is find the adjoint of dou by dou theta, where theta is the polar angle. Is the polar angle in spherical polar coordinates. Spherical polar coordinates. Okay, so the first exercise. And second exercise is rather simple. Find the adjoint. Find the adjoint of dou by dou r, where r is the radial coordinate in cylindrical coordinates. Cylindrical coordinates. And third, of course, find the adjoint of x d by dx operator. Okay, x is multiplied with d by dx. Okay, so these three exercises will probably give you an important I may call skill of finding the adjoint of an operator. Okay, now we will define what is called self-adjoint operator. We will define something called self-adjoint operator. Now, an operator A is self-adjoint if and only if okay, I don't have to write if and only if, because this is just a definition. If is self-adjoint if A dagger, that is the adjoint of an operator, is equal to B. Okay, an operator A is self-adjoint if A dagger is equal to A. Now, this has two parts. Okay, so please understand this. A dagger is equal to A. This implies this has two parts. Now, the first part is that for any pair psi of x, phi of x in the Hilbert space H, psi of x comma A acting on phi of x should be equal to A psi of x acting on phi of x. This is basically the definition of the adjoint, right? This is basically the definition of the adjoint. Okay. Now there is a second part to this. The second part comes from the definition of our first we have defined. You see, when do we say two operators are equal? When their domains are same. Okay. So the second condition is that the domain of A has to be equal to domain of A dagger. Okay. Why we are explicitly mentioning this is that we will make a remark here. Remark is that in general, domain of A dagger is a superset of the domain of A. So domain of A dagger is a bigger set than A. Okay, so that means the second condition is not satisfied. Okay, so that implies 2 is not satisfied. In such a case, A is called, that means only one is satisfied but two is not satisfied. In such case, A is called a symmetric operator. It is called a symmetric operator. Now, if 1 and 2, if 1 and 2 are both satisfied, if 1 and 2 are both satisfied, then A is called, A is self-adjoint. A is self-adjoint operator. Okay. Now, let's talk about finite dimension. So, finite dimensional case, as we have already said, that your A dagger, finite dimensional case, A dagger is basically A transpose conjugate. That's what we have said, Hermitian conjugate. Okay. And if A dagger is equal to A dagger is equal to A, then the matrix is called Hermitian. Okay. Now, so here E of A is equal to D of A dagger always in finite dimensional case. So this in between category of asymmetric will not happen. Okay, so if this Hermitian conjugate is fine, then it is called a Hermitian matrix. So sometimes we say Hermitian matrix, but Hermitian operator, but Hermitian operator and self-adjoint operator are Hermitian operator is the usage only used in finite dimensional cases. In the infinite dimensional cases, since this difference is there, we will always call this as a self-adjoint operator. So self-adjoint operator, so in finite dimensional vector spaces, both symmetric operator and self-adjoint operator, both of them are called Hermitian operators. Whereas in infinite dimensional cases, we make this distinction that a self-adjoint operator is a symmetric operator, but a symmetric operator is not a self-adjoint operator because these domains are not same. So let me give you an example to illustrate this point. Suppose now we consider, so an example. To illustrate this point, so let us consider an operator A is equal to minus I d by dx. Suppose you consider an operator I like this. Okay. Now we have seen that, so what will be your A dagger? A dagger, as we have seen from our previous analysis. Okay, so let us say consider an operator space on L2 of R, on this space. A dagger will be equal to, so it will be minus I. For the complex number, it will be simply complex conjugate, and d by dx dagger. It is equal to I times minus d by dx. I times minus d by dx is equal to minus I times d by dx. Okay. So that means A is self-adjoint. Because your both domain is the domain of A and domain of A dagger is full vector space. Okay. So in this case, domain of A is same as domain of A dagger, which is equal to L2 of the full space. Now let us consider the same operator A is equal to minus I d by dx on, let's say, L2 of some interval AB, some finite interval AB. AB will be some finite interval. This is a subset of real line. Now, suppose if we are interested in finding this out, so let us go back to our analysis of this adjoint. Okay. So let us consider this. So let's say f of x, comma, minus I d by dx, g of x is equal to integral a to b, because now the functions are defined in this interval ab, f star of x into minus I d dx acting on g of x Okay, so now let us try to look at this expression. We have to do an integration by parts. So let's look at the integration by parts. U is equal to, okay, let's call this as minus I into f star, and dv is equal to dg dx into dx. So v is equal to g, and du is equal to minus I dx. Okay. Yeah. So that is fine. So this is equal to, we get minus I into f star of x into g of x from a to b minus integral a to b minus I df star by dx, into dx here, into g of x. So this one, I will call this term depends on some a and b. So let me call that as some delta of a comma b plus integral a to b I d by dx into f star of x into g of x. Or I can write this as delta a comma b plus integral a to b minus I d by dx into f of x, the whole star. Because when I take whole star, this minus I star becomes I, and this is what I will have here, into g of x dx. So which is equal to delta of a comma b plus, this is an inner product of minus I d by dx into f of x. Yeah. So you see, I started with this operator and I got this operator. Now, if this delta AB is equal to 0, then I can say that this minus I d by dx is a self-adjoint operator. Okay. So note that A is equal to minus I d by dx is a self-adjoint operator. Self-adjoint operator. Okay. I must say that is a symmetric operator. The symmetric operator if delta AB is equal to 0. Okay. Further, A is equal to minus I d by dx is self-adjoint if the domain of A is same as domain of A dash. Now, first we ask this question that for delta of AB to be equal to 0, okay, we must choose functions in L2 of A comma B such that how do we choose? So let us write what is delta of AB. Delta of A comma B is equal to minus I f star of B d of B minus or plus I f star of A into G of A. Because this is what is the expression. If you substitute the limits here, you substitute the limits in this equation, this is what I am calling it as delta A. So such that if I choose in such a way that f of A is equal to f of B is equal to 0. Suppose if I choose something like this, then I can say this will be equal to 0. Okay. If I choose functions like that, then I can choose that to be equal to 0. Okay. So now what I'm trying to say is that when we are taking in the sorry, I think I should write this. As that G of A, G of B is equal. Okay. Now the point is that when we are taking this, when we are taking this f of x, comma A G of x, when I'm taking this, okay. Remember we talked about a vector space. So these are like elements of the vector space. Elements of vector space. Okay. And what are these? These are basically elements of the dual space. They are basically linear functions, as we have seen. Okay, so in general, you see this. Sometimes the dual is same as that space, so that is basically the same vector space can be the dual of itself, but it is not necessarily true in all the cases, right? So in that sense, the domain of A is a subset of vector space, and domain of A dagger is a subset of dual space. Okay. Now suppose if I am choosing my vector space like that. So suppose if I choose my domain of A as set of vectors or functions. Okay, so let me call this as g of x in L2 of AB, L2 of AB, such that g of A is equal to g of B is equal to 0. Suppose I choose my domain of A to be like this. Okay, and I could have chosen my domain of A dagger to be full of L2 of AB. Okay, I could have chosen this like this full space, and this is only a subset. Now, if I choose DA and DA dagger like this, okay. Now, for this choice, okay, notice that delta of AB is equal to 0. Delta AB is equal to 0 because it is sufficient. No, if G is 0, it is sufficient for me. G of A is 0, G of B is 0. That is enough. F of A and F of B need not be 0. So delta AB is equal to 0. So this tells you that your DA and DA dagger is not same. So what happens that the operator, the conclusion is that the operator A, which is equal to minus I d by dx, on L2 of A comma B is symmetric, but not self-adjoint. Because EA is not same as okay. So that is the example that I was difference that I am saying in terms of these operators for the infinite dimensional case. For finite dimensional case, such a discrepancy does not arise. Okay. So now the question is that when we are dealing with especially this compact intervals, we have to be careful in talking about self-adjointness. If it is the full space L2 of R or L2 of C, whatever that we L2 of R when we are considering, then there is no problem. But when you have this finite interval, then there is a some kind of a care is required to understand that whether a given operator is self-adjoint or not. Okay, so now we are ready to write down our what is called postulate 2 of our quantum mechanics. Postulate 2, and postulate 2 is physical observables. Physical observables okay. What do you mean by physical observables? They are some kind of a measurable properties. measurable properties. Of a quantum system are represented by a self-adjoint operators acting on Hilbert's. So physical observables of a quantum system are represented by a self-adjoint operators acting on Hilbert space. So for every physical observable, we will have a corresponding self-adjoint operator. Now, what is self-adjoint operator is what we have discussed so far. How to find adjoint of an operator and how to make a self-adjoint operator is something that we have already discussed. Now,
Here, sir.
yes.
So do every operators have their adjoints, or is there any example where the operator don't have adjoints?
You can write so actually the procedure that or the definition that we have given, you can construct an adjoint for every operator. Okay, but whether that adjoint is same as,
So if every operators have adjoint, then how to interpret that physically? Like what does the adjoint of operator, every operator would mean? Like suppose if I have operator for angular momentum and its adjoint exists. So what does the adjoint of angular momentum operator means?
So basically, if you have, see, angular momentum is a physical observable, and if you have physical observables, then the operators corresponding to them will always be self-adjoint. That means adjoint and that operator will be same. So if at all you have an operator which is not a self-adjoint operator, then that does not correspond to any physical observable. So that may be some mathematical operator which you may define, and it may have some relevance, but it is not going to represent any physical observable. So what I'm trying to say is physical observables are always represented by self-adjoint operators. So that question does not arise that if operator represents this physical observables, what will be its adjoint represent? You follow, right?
Yes, sir.
Okay. So now this has an interesting interesting thing that we have in general. Okay, so at this point, let us say that we have important thing to learn about these operators. So an operator, so even in general, for some psi of x, the Hilbert space H, an operator A acting on psi of x is equal to phi of x. So it's, the action of an operator is to change the state to some other state. But for every operator, A, for every, let's call linear operator, A, there are some states. So let us call them as some phi n of x. Such that when A is acting on this phi n of x, the state will not change, but it will simply be scaled by a scalar. Okay, so this is something which will for every operator, some states will be there which don't change. Okay, so in that case, we say that this phi n of x is called an eigenfunction of A. An eigenfunction is a German name, eigenfunction. Eigenfunction of A. And this an is called an eigenvalue of A. So this is something similar to what you know in matrices, eigenvalues and eigenvectors. So eigenvector is a generalized as an eigenfunction, and an is called an eigenvalue of A. Okay, once we have this situation, then we have an important theorem. Okay, this theorem has two parts. Part one is that eigenvalues of a self-adjoint operator are real. So in general, eigenvalues can be complex, but if you have self-adjoint operator, then the eigenvalue of self-adjoint operator are real. Now let's try to prove this one. So consider the definition of self-adjoint operator. That is, we have for any pair of states, namely psi of x and phi of x in the Hilbert space, because A is Hermitian, psi of x, A phi of x is equal to A psi of x, phi of x. Why? Since A is equal to A dagger. Since A equal to A dagger, I have written this. A here also, A here also, and A here also. Otherwise, I would have written A dagger here. Now, let us say that some functions, which I will call it as some chi n of x, okay, be eigenfunctions of A, okay, with eigenvalues. Sometimes we call this as eigenspectrum an. What does that mean? That means A acting on some chi n of x is equal to an chi n of x. Now let us consider, so let us set psi of x is equal to chi n of x and phi of x, because this is true for any pair of functions, I will take both functions to the same chi n of x. Okay, so in the definition, then what we will have this quantity chi n of x, A acting on chi n of x is equal to A chi n of x comma chi n of x. So I'm going to take both for psi and phi chi n of x. But what is this one? Because this is an eigen function of A, this is nothing but chi n of x, comma a n into chi n of x is equal to same thing here, a n chi n of x, comma chi n of x. But notice, if I have this is just a number, okay, scalar. If I have to pull out a scalar, it implies this is equal to a n into chi n of x, chi n of x. Now, if I have to pull out this a n from here, then I will get a n star, okay, into chi n of x, comma chi n of x. Okay. Now you see this chi n of x and chi n of x on both sides, and that is not zero. Okay, that is not zero because this is the norm of chi n. Norm of any vector is zero only if that vector is zero. So for any non-zero vector, this is not equal to zero. So that means this is basically a n minus a n star into chi n of x and chi n of x is equal to 0 if I take it to the other side, and since chi n of x is not equal to 0, implies a n is equal to a n star. So a n is equal to a n star means what? The value, eigenvalue is equal to its complex conjugate. It implies a n real, and n is arbitrary, therefore all the eigenvalues of Hermitian operator are real. So this is the proof of the statement 1. The eigenvalues of a self-adjoint operator are real. Now the statement 2 that I want to write as a part of this theorem is that eigenfunctions of a self-adjoint operator corresponding to distinct eigenvalues. Are orthogonal. Corresponding to distinct eigenvalues are orthogonal. Now the proof of this one is also simple. So what I will do is, so I go back to the same definition. Okay. So now let us set psi of x is equal to some chi m of x, and phi of x to be equal to some chi n of x in the definition. Now a on chi n of x equal to a n into chi m of x, and a acting on chi m of x is equal to a m into chi m of x. Okay. Both are eigenfunctions of A. Then if we set this one, then we have chi m of x, a acting on chi n of x is equal to A acting on chi m of x, chi n of x. Okay. Now that is it. This implies I have chi m of x, a n chi n of x is equal to a m chi m of x, chi n of x. Okay. So I could write this as a n into, let me simply suppress this x chi m chi n. This is equal to, I should write am star, but we have already proved earlier that am star is same as am. So I pull out am and then write this as chi m comma chi n. So this implies I get here, I take this to the other side, an minus am into chi m of x comma chi n of x. Okay. This is equal to 0. Now, since we are talking about eigenfunctions corresponding to distinct eigenvalues, okay, so distinct eigenvalues implies an minus am is not equal to 0. So that implies the inner product of chi m of x comma chi n of x is equal to 0. That implies chi m of x and chi n of x are orthogonal. Okay, so we can see that eigenfunctions of a self-adjoint operator corresponding to distinct eigenvalues are orthogonal. So these are the two things that we have proved that of a self-adjoint operator. Now comes the important physical, physically important statement. The statement is that if a physical observable is measured, the result will be one of the eigenvalues of the corresponding self-adjoint operator. Okay. If a physical observable is measured, the result will be one of the eigenvalues of the corresponding self-adjoint operator. And your measurement results have to be real. And since this is going to be the physical correspondence, then you have, suppose I measure some energy of the system, and then I should get so many electron volts or so many trees, whichever unit that you are measuring. Okay, but I should not get it as some 2 plus 3i or something like that. So we will not know how to understand that result or interpret that result. So it is better our theory is constructed such that the measurement results are always real numbers. and that is that is what the correspondence between the elements of theory and the physical reality. So this is the correspondence. But the interesting point here is that we have I think it's okay. So let me stop here. We will pick up from this point on Monday, and then we will try to discuss a little more structure related to this postulate 2. So we have, so the postulate 2 is essentially how a physical observable is represented and what does that mean. So it's a self-adjoint operator. It has real eigenvalues and orthogonal eigenfunctions corresponding to distinct eigenvalues. And this will help us to formulate the theory further and then talk about what happens when we measure the system. I will stop here if there are questions.
Hello, sir.
Yeah.
Sir, I have a doubt.
Mhm.
As corresponding to all physical observables, operators need to be self-adjoint, as eigenvalues should be real. But sir, in a previous example, in the infinite dimensional case, there are some discrepancy has arisen. It is not self-adjoint. So what should we consider a finite dimensional space or infinite dimensional case?
No, most of the times our physical examples are infinite dimensional spaces. Okay, so we have to either consider the infinite dimensional vector space such that the operators are self-adjoint, or we have to consider a subsets in such a way that the domain of A and domain of A dagger are same.
Yes, sir. So we have to choose accordingly so that operators are self-adjoint.
Correct.
Yes.
For example, on the L2 AB case that I discussed, suppose let us say that you don't consider L2 of AB, but you consider only that space for which all the functions will vanish at A and B. That is, your boundary condition is such that for all functions f of A is equal to f of B, and that is also the domain of A dagger. If you take like that, then it will become self-adjoint there.
Yes, sir. Thank you, sir. Sir, another doubt: the Del operator in three-dimensional is self-adjoint or not?
No. See, d by dx operator is also not self-adjoint, right? Even d by dx dagger is minus d by dx.
Yes, sir.
Correct. So del operator also will have the same features in 3 dimension.
Yes, sir.
So it is not self-adjoint.
Yes.
Yeah.
Hello, sir.
Yeah.
Hello.
Yeah. Go ahead.
Sir, can you share group theory lecture number 3? I missed that class.
Lecture number 3, yeah. If possible, can you just send me the date?
Sir, I think April 5 or 6.
Okay.
The last section of the previous class is Lagrange's theorem.
Okay. I will share.
Okay, thank you, sir.